So, we're also going to talk about one-sided limits. You've just not seen the notation for it before, but we knew for a limit to exist, it had to meet up from the left and the right of the point. So here's the notation for this. The limit as x goes to c with a positive superscript means from the right. Or from the positive side of the number line. Right? So if we have a number line or an x-axis, if that's 0, then my positive numbers are over here, my negative are over there. So it means I'm approaching from the positive side from the right. The limit as x approaches c with a superscript negative means from the negative side or from the left. So I can ask you to give me just one or the other instead of telling me the limit in general. And we already know this, we just didn't have formal notation for it. But the limit as x approaches c in general is equal to the same thing as the left and the right if and only if. That's what this means right here. Any of you ever seen that before?
No. No.
That's the answer I always get. And when I write it on the board by hand, everybody thinks I just made a mistake.
I thought you were trying to write different, or like diff, but like just not the D.
No, it means if and only if. I'll explain that in a second. The limit from the left and the right, so this is the limit from the right, are some finite y value and they match up. Okay, we already knew this, we just didn't have a formal definition. Okay, so we're just going to find some one-sided limits. Guess what? You do the same thing you did with all the regular limits. We do direct substitution. So, find the limit as x approaches -2 from the right just means we're going to direct substitute -2 in there and see what happens. Well, if we put a -2 in there, I get the square root of 4 minus 4 equals 0. That's my answer. Doesn't matter whether it was coming from the left or the right. The limit as x approaches 5 from the positive side, we do a direct substitution. And we're going to get 0 over 0, right? We manipulate it the same way. If I factor this, the denominator is a difference of squares, so I get x plus 5 times x minus 5. I'll simplify that, and we get the limit as x approaches 5 from the right of 1 over x plus 5. I do a direct substitution and we get 1 over 10. So it didn't matter whether I was coming from the left or the right, that one was going to be the same. Okay, on this one, the limit as x approaches -3 from the left. Well, if we do direct substitution here, I'm going to get -3 over the square root of -3 squared minus 9. Stop. Is -3 over 0. What do we say?
Does not exist.
Does not exist. Okay, and that's actually a pretty interesting one to look at what is the domain of this function, I would need x squared minus 9 to be greater than 0, right? Can't divide by 0 and can't have a negative number under the square root. Well, that means x squared is greater than 9 and x is greater than 3 or less than negative 3. Okay, now how do I decide whether it's in between negative 3 and 3 or outside? Pick a point. If we plug in 0 into this function here, I get square root of negative 9, right? So my function can't exist in between, it exists on the outside. Which means if I'm coming at negative 3 from the left, we're over here. Why did I get does not exist? Oh, because it's in the denominator. And we're landing on it. Right? We're trying to land on the open hole. So it does not exist. Okay. The piecewise function, these are a little bit trickier. The left and the right now matters. So we're looking at what happens as I approach 3 from the left. Okay, well, on a number line, the left of 3 is over here. So it's numbers less than 3. So I have to decide, do I need row 1 or row 2 of my piecewise function to evaluate? Row 1. So we're going to plug in a 3 to row 1. And I get 5/2. So that means the limit here from the left is 5/2. If I asked you for from the right, we would have used row 2.
Okay, so that's just fluff. That's just there to throw us off.
No.
But if we're only approaching from one side, that means we just do the other half, right?
Right, but this is to build up to being able to tell me, is it continuous? So if instead of me just asking you for the one-sided limit, I asked you, is it continuous, you would check both sides, right? So the value of this example, because most of it's just direct substitution, right, is just making sure you understand the notation.
Gotcha.
Okay. The limit as x approaches pi over 2 from the positive side of secant x. Well, what is secant? So let's rewrite that, because if I got to figure this out from the unit circle, I need to be in terms of sine and cosine for me to know off the top of my head, right? What is cosine of pi over 2? 0. So, does this limit exist? No. Because cosine of pi over 2 is 0. But let's look at what we're discussing here on a graph. If I were to graph cosine, which you're supposed to do in order to graph secant, oops, I meant that would be pi. Then my graph of cosine, it starts high, right? At pi over 2, it goes to 0. At pi, it goes low. 3 pi over 2, back to 0. Goes high again. So we see we're coming from the right. So I'm coming here towards 0. But that's not the important part. But to remind you what secant looks like, If it's 1 over cosine, it matches up at the positive and negative ones. At zeros, it has vertical asymptotes. Right? So that's why we got the does not exist, because we got a vertical asymptote there. It's just a refresher for you about what the graphs are and what they look like in the unit circle. Okay, so then you're going to have some problems that say describe the intervals on which f is continuous.
Okay, so all right, I got a question about the last one. So is secant ever going to be continuous, just in general?
It can be continuous at a point. What if I had asked you about pi over 4?
Oh, okay.
At that point, it would be okay, right?
Yeah. Okay.
Okay, describe the intervals on which f is continuous. I put this in here so that you'd see the wording that you're going to see in the homework. When they say intervals, that means they're asking for interval notation, versus in the first example, we just talked about the continuity of the problem. Here we got to describe the intervals. So again, we start off by finding the domain. So for this function, what is x not allowed to be? Does it have any other issues? So my interval of continuity is going to go from negative infinity to 6, but not include it, right? Because can't land on it. And it's also continuous going from 6 to infinity. F of x equals x squared minus 4x plus 4. So just think about that function. What does it look like? It's quadratic, right? It's parabola. It opens up. There going to be any discontinuities? No. It's continuous everywhere, which we're going to write using interval notation as negative infinity to infinity. Okay, there's no denominators, there's no square roots. That has a domain of the whole real number line. It's continuous everywhere. Okay, in the next one we got piecewise. When I look at row 1, that's a line with a slope of 1/2. So by itself, that line would be continuous everywhere, right? And if I look at the second row, that's another line with a slope of -1. So by itself, that's continuous everywhere. So we just have to check and see, do they match up when x equals 2? That's my only spot that I might have a discontinuity. So if we plug in a 2 here, I'm going to get 1/2 times 2 plus 1 equals 2. And if I plug in a 2 in row 2, I get 3 minus 2 equals 1. So we have a jump discontinuity, right? And if we're talking about where is it continuous, it's going to be everywhere but at 2. So we're going to go from negative infinity to 2 and 2 to infinity.